In this video, I'm going to review for you what I call the fundamental law of population dynamics. And here it is. Arguably, the entire course can be distilled down to understanding this equation. The top form of it simply says delta n, that is, the change in numbers of a population, is equal to the number of births minus the number of deaths plus the number of immigrants minus the number of emigrants from the population. If we think about the unit of time over which this change is being calculated as shrinking down to an infinitesimally small unit, we can rewrite this as a set of rates where we have n prime, which simply says the instantaneous rate of change in n is equal to little b times n minus little d times n plus I minus e, where b and d are now per capita instantaneous rates of change of births and deaths. Let's consider one piece of that equation for the moment. We just look at the instantaneous rate at which deaths occur. So n prime is equal to minus d times n. If you recall back to your introductory calculus, what we have here is an equation describing the rate of change in n as a function of n and a constant. That is simply the equation for exponential decay in this case, because the constant has a minus sign in front of it. And the solution to this equation is quite simple and very fundamental to what we want to do in this course. We can calculate n at any future time t is going to be n at time 0 times e raised to the power minus dt. That's the solution to the equation for exponential decay. And if we can plug in an example, imagine that we release 10,000 fingerling fish into a lake as part of a stocking program. And we know from previous research that the per capita rate of death of those fingerlings on a weekly basis is 0.01. So our per capita rate D, 0.01. And what we want to know is, after 1 year, how many fingerlings do we expect to be alive? So 1 year is 52 weeks. Our rate has been calculated on a weekly basis, so we need to use 52 there. And if we simply grind through this equation, we come up with the answer of 5,945 fingerlings 52 weeks forward in time. Now we know that's not exactly how many there will be in any particular release case. What we've calculated here is an expected value. There's many different random events that could occur between time 0 and time 52, and how many fingerlings, for example, get eaten by catfish simply is an unknowable quantity. We know that some will, with catastrophic results for the fingerling, but we don't know exactly how many. What we have here is an expected value over that time frame. Now let's add in both the birth part of the equation and the death part of the fundamental law. Peter Turchin, an ecologist at the University of Connecticut, calls this the law of population inertia. And if we rearrange things a little bit here, we can say, so we have b per capita birth rate times n minus d times n. We take n out of that, we get b minus d times n. And this combination of the instantaneous birth rate and the instantaneous death rate, we give a special symbol to, little r, and we call that the intrinsic rate of population growth. What it says is that all other things being equal, the population will either grow or decline in proportion to this intrinsic rate of population growth. Following along from before, we can write this down as a simple equation. N at some time t is equal to n at the beginning times e raised to the power r times t, the number of time steps forward. This is the equation for exponential growth of our population. The population will grow if little r is positive, that is bigger than 0, and will decay if little r is negative or less than 0. Looking back here, we can see that those two conditions correspond to whether the birth rate is greater than the death rate or less than the death rate. We can look at these equations graphically. If we imagine that n naught is equal to 100 and little r is equal to 0.1, we would get the following curve where after 20 years the population would have increased exponentially to well over 600 individuals. In contrast, if little r is negative 0.1, then the population decays towards 0. It's a useful property of exponential growth that if you take the logarithm of both sides of that equation, you're left with the equation of a straight line. So that's what we see here. Starting at n naught equals 0, our population either increases with a slope of 0.1 or decreases with a slope of negative 0.1, depending on whether our population is growing or decaying. We can use this feature of exponential growth to do a couple of things. One would be to estimate the size of little r, and the other is to detect departures from exponential growth. If we plot our population size over time on a log scale, and its population is either growing or decaying exponentially, we should see a straight line. This constant, little r, the intrinsic rate of population growth, is very important, and so we want to figure out how we can get estimates for this. One simple way to do it is if we have population size estimates at two different times. If we take our exponential growth equation and rearrange it a little bit, so now we have nt and n naught. We've divided both sides by n naught. We take the logarithm of both sides, so now we have the logarithm, the natural logarithm of nt over n naught is equal to little r times t. And then we simply divide both sides by t, and we get this equation for the intrinsic rate of population growth. It's simply the logarithm of the ratio of population sizes divided by time. Musk oxen were widely distributed across the Arctic in both the Old and New Worlds, and their populations declined until the middle of the 20th century when they were protected and then populations began to recover. This particular musk ox is in Alaska. A biologist with the Alaska Department of Fish and Game surveyed the muskox population at Nunivak Island starting in 1947, going through 1968. He observed 49 animals in 1947 and 514 animals in 1965. Using our equation, little r is equal to the logarithm of nt over n naught divided by t. We can calculate simply by plugging in these numbers, 514 divided by 49, divided by the number of years, in this case 18. And we come up with an estimate of, for little r, of 0.13, and the units are years to the power minus 1. We can use this estimate now of little r now to figure out, for example, how many muskox will there be in 3 years, assuming that the per capita birth and death rates do not change from their average value over the previous 18 years. So now we simply plug in n naught is 514, our estimate of little r is 0.13, t is 3. We calculate this part and we see that we expect the population to increase by a factor of 1.48, which gives us 759 muskoxen in 3 years. Another question you might be interested in is how long for the population to double in size. In fact, there's nothing special about doubling. The question could also be how long will it take a population with a given rate of intrinsic population growth to change by 10%. But let's start with doubling. Doubling simply means that we're going to have 2 times whatever we started with. So we plug in 2 times n naught into our equation for exponential growth, and you can see that the n naughts cancel out on both sides, and we're left with a constant 2. Take the logarithm of both sides, divide by little r, and we're left with a relatively straightforward equation. The log of 2 divided by little r will give us the time required for the population to double in size. For our muskoxen, that means we have a population that we divide by 0.13, and that's going to give us a doubling time of 5.3 years, which seems very short for such a large animal. In a previous slide, I predicted that in 3 years there would be 759 muskoxen, assuming that the per capita birth and death rates remained constant. In fact, in 1968 there were 714 muskoxen, not 759. So what went wrong with our equation? Well, the most probable thing is that our per capita birth and death rates were not constant, but in fact have deviated from the average that we have seen over time, and that'll be the topic for the next video. The other thing to keep in mind, of course, is that if our populations have been counted with some degree of error, then our estimated population size of 514 may have been inaccurate. And in addition to that, our observed population size in 3 years may have been inaccurate. So both of those things together could conspire to lead us to have a difference in our population size than we expected from the exponential population growth equation.